are volcanotourism on these basaltic places like Hawaii and Etna and so forth. So it's important to understand how these eruptions may take place and the underlying physicochemical processes. So just to have all of us on the same page, I know it's a volcanology seminar, but I know a lot of probably a different background. So typically for magmatic eruption that is driven by magmatic volatiles, that volatiles dissolved in the magma, there are basalt typically erupts like lava flow, effusive eruptions, or Hawaii or fire fountain. In this case, that's the example that you can see. And also like Strombolian style eruptions, which are regarded as mildly explosive eruptions. Now, you probably are familiar with the recent eruption, Hawaii, this lava flow, that the socioeconomic destruction that it has caused. So one can only imagine that if this is a Plinian style eruption, for example, like a very highly explosive eruption, that would create even more damage. And it's important to understand for volcanic hazard assessment. It can be viewed sort of as that classic example of Mount St. Helens in 1980. I don't have a better figure of this basaltic plain eruption. So there are more and more work that are coming out recently, and that's very exciting, that are looking into different places of this subplinian to plinian style eruptions of basaltic magma, which are much higher explosive than what typically are more dominant style of basaltic eruptions. So here there are two examples that I'm showing, like Taraira, Mount Taraira and Mount Etna, but there are, as I said, like there are other examples as well. So based on stratigraphic study, it has been noticed that the eruption column in these eruptions were 20 to 30 kilometer high, and the volume of deposit is up to 10 cubic kilometer. And based on this observation, it has been defined as Plinian style eruption. So the Plinian style eruption also typically is associated with the brittle fragmentation of magma. That sort of is also based on, partly based on the observation of the clast itself, that the typical clast on the left-hand side, if you can see my cursor, that's the fluidal pyroclast, which is from Kiloyaiki 1959. So it's Pelly's hair and all these fluidal textures, which are sort of more hydrodynamic fragmentation. As opposed to this class, this is from Etna 122 BCE, class from courtesy Dr. Bruce Houghton. It has this rack texture and structure. You can also see those melts in the pore space is sort of fractured in a brittle-like manner. So the question is really that how a liquid like basaltic magma can fragment in this manner. To understand that, again, to have us all on the same page, just a few background on this. So this is a very simplified schematic cartoon that shows that magma ascending from a magma chamber to the surface. There are many processes that are happening: bubble nucleation, growth, fragmentation. As magma is ascending, pressure is decreasing, volatile solubility decreasing, and it's dissolving into a gas phase. If you have if you were present at Sahan's talk a few weeks ago, he was talking about the bubble nucleation within chamber as well. But the idea is that, like, as magma is rising upward, it's sort of that volatile solubility decreases and it diffuses into the existing bubbles, or it creates these new bubbles. And these bubbles act as the pressure bomb. So the presence of bubbles are really key, because that sort of decides whether magma will come up as a coherent body like a lava flow, or it's going to be a more like a gas pyroclast flow. And as the bubbles are rising upward, it's sort of creeping that pressure within it. At certain depth, when that pressure exceeds the strength of the magma, it breaks it apart. And viscosity of the magma plays the key role here, because that hinders this bubble growth. So bubble is growing in disequilibrium. It's sort of preserving that pressure within it. And most of this, the existing criteria for fragmentation, stress or strain rate dependent criteria, are more or less sort of relates inversely to viscosity. So as viscosity increases, it has more chances for this explosive fragmentation because of this keeping the pressure within the bubble. Now on this figure, it's a viscosity and log scale as a function of water in dissolved water in magma in the melt. The red is for basalt and the blue is for rhyolite. That's more silicic magma here. Sorry about the cursor, sometimes it's just not coming up. So the key here is that like for at any given water content, the viscosity of the basalt, it's at least 4 to 5 orders of magnitude lower than in the case of rhyolite. So that means that the basalt is not being able to keep this pressure within the bubble. And that's why typically those the basaltic eruptions are not associated with high explosivity. And also the bubbles can escape the system because if the viscosity is low, it can rise and escape. So therefore, it's not being able to preserve that pressure. So that kind of raises this question that how this liquid-like and less viscous basalt can fragment in a brittle manner. That's sort of the question that I wanted to address. And so the observation of this pyroclast, so pyroclast is the only direct evidence. So as I showed one of those pyroclasts, now this is under thin section in 2 dimension. It's a scanning electron microscope image of both Mount Taraira and Mount Etna. And if you look at this inset, that shows those elongated lathe-shaped structures. Those are crystals, mostly plagioclase crystals, and also it has equigranular pyroxene and olivine crystals present in it. This black area is vesicle, and this is the matrix surrounding it, which is melt plus crystal surrounding it. That's the gray area surrounding it. Now, the crystal content, it's about 60 to 90%. So it's more than 60% in these eruptions. And based on the previous studies, it has been hypothesized that these crystals also experimentally has been shown that this must have formed during eruption. So it's a syneruptive crystallization, this micron scale small crystals. So the idea was that like how these crystals might have played a role in these eruptions, and whether they have changed the viscosity of the magma, or if the change in viscosity is the only reason behind this fragmentation. So in order to address that, I did dynamically similar experiments. Dynamically similar meaning that there are force balances, the forces that are acting in nature and the forces that are acting in the experimental setup based on dimensionless numbers. So the experimental results in principle should be applicable to the natural setting as well. So I used silicon liquid and solid particles of different size and shape to simulate as analogous to the crystalline basalt. So just to go back to the previous slide, the distribution that I have found in this texture are mostly bimodal broadly. Those are really those elongated particles. Those are plagioclase crystals, a high aspect ratio, and there are equigranular crystals or even small plagioclase crystals that are present in between those. So what I would like to see that how this distribution of a different shape and sizes of particles can change the rheology of the magma. Now, it has been shown by a number of studies previously that the maximum packing of this particulate system has implications for the viscosity of the magma. So the maximum packing is really what is the volume of particles that can be fit in for a given volume in a given volume of container. So here I used a geopic instrument that sort of gives a transverse force, and knowing the volume of that chamber as well as knowing the volume of the particles, the maximum packing can be figured out. Now, most of the existing literature, the maximum packing has been used as a fitting parameter to the rheological results. In this case, I took a little bit different route that I measured the dry maximum packing of these particles, which is without any liquid, and then use that in the rheological experiments. So just to give some upshot of this maximum packing, here it just shows the maximum packing as a function of volume fraction of small particles. And if you just, and for different proportion of these two particles, the maximum packing changes. But if you look at these two images on both the sides, here it shows two spherical particles. One is large, one is small. The thing is that like the smaller particles fits in those void spaces in between the larger particles. So the maximum packing can go up as high as 80%. On the other hand, on the right-hand side, this is a unimodal distribution of this high aspect ratio particles. And what it shows that it creates those caging and void spaces, so in a random distribution, and it hinders for more packing. So the packing is only about 30%. Now it's very important because as I will show in next few slides, this maximum packing which controls this viscosity. So knowing what are the sizes, what are their distribution in the magma is important because that can have a wide range from 30 to 80% or even higher. So now I take those particles that I know particulate system, that I know the maximum packing. I use the silicon liquid that I showed before, I mentioned before, and I prepared a suspension, placed it within a rheometer. So this is a rotational rheometer, and the sample is placed in between two plates. The upper plate rotates. It's a torque that is applied from where the shear stress is calculated. And from the angular velocity, the rate of deformation of the strain rate or shear rate is calculated. So from there, the shear stress and strain rate relationship can be obtained. And the best way to do it is using this Herschel-Bulkley model. That relates the tau, which is a shear stress, with the yield stress, that is tau y, which is a minimum stress that is required to deform the material. K is the consistency, which is in the absence of any nonlinearity or absence of yield stress or non-Newtonian behavior. It's similar to a viscosity, so how thick the material is. And N is the flow index. So that sort of defines, in all these experiments, what I have found, it's a shear thinning behavior that sort of shows that as the rate of deformation increases, the viscosity of the material decreases. Now, just to have a couple of slides on this, so here I'm showing some of the results that shows the consistency, as I mentioned in the previous slide, divided by the viscosity of the suspending liquid. So that's the normalized consistency as a function of particle volume fraction. And as it shows that as this maximum packing increases, this exponential curve, so that viscosity sort of increases exponentially, and that flattens as this maximum packing is increasing for this different particulate system, from unimodal to bimodal system. All the symbols mentioned represents these different particulate systems. Now, as I plot the data as a function of normalized particle volume fraction, which is this particle volume fraction divided by the maximum packing of that particular system, which I measured, the data more or less plots on a single line. So it shows that this exponential kind of relationship can be used for any sort of particulate matter, like for crystal size distribution, whether it's unimodal or bimodal distribution, to predict and calculate the consistency as a function of the volume fraction of particles, knowing the maximum packing of the particulate system. This is, I don't have any numbers here. This is just showing that it's a bit more complicated than that, because as I mentioned, that it is a non-Newtonian behavior. So therefore, it has yield stress and other non-Newtonian properties. Mainly, it's a function of rate of deformation. So this is a three-dimensional plot that has another axis here, shear rate. So it's a viscosity as a function of shear rate and the crystal fraction. And the upshot here is that the viscosity sort of decreases as the rate of deformation increases. So that also is required to be included in a model of a magma flow of magma in conduit or in the magma chamber with crystals. Now, so I got the viscosity increase by 4 to 5 orders of magnitude from this results. But the question was really that, is this enough to fragment this basalt into pieces? And my understanding is that it's not possible, because the thing is that the melt in between those crystals is still basalt. So it's still those less viscous basalt that is in between those crystals that needs to fracture. So it must have changed the bulk property in a way that it can fragment in a brittle manner. So along with this rotational studies like oscillatory shear studies that sort of to understand the viscoelastic property of this crystalline particulate system, which I'm not going into here, I also tested this using a tensile tester where I placed the sample, same particulate suspension in between two plates, and the bottom plate is stationary, the upper plate sort of gives an uniaxial deformation. The video, and using video images, I can measure how this mid radius, which is d mid here, it sort of changes as a function of time. And also the separation length, which will give rise to the strain and strain rate, is also changing as a function of time. So this sort of simulating, if you can imagine a situation where in an expanding magma, the bubble is growing, and so the melt surrounding the bubble is also getting stretched as the bubble is growing. And so that stretching of the melt, if it goes too far, that might create a scenario where the melt can fracture due to this rate of deformation. So the upshot of this calculation is that so here it shows extensional strain as a function of extensional strain rate. And what I observed is that at a higher rate of deformation, this suspension that fractures in a brittle-like manner. So this fracture is angular, and there are irregularities, and this is reproducible. At an intermediate strain rate, it does fracture, but it fractures in sort of a ductile manner. So it gradually forms that necking, and then it sort of breaks away. And at even lower strain rate, it doesn't fracture, it just gets stretched. Interestingly, that suspending liquid, the liquid without particles, even at this higher strain rate, it doesn't fracture. It has that thin filament that is very typical of this powder class, 1 micron filament of this melt films that are often observed. And so those that is also observed here, that the liquid doesn't fracture. As soon as I have this suspension, the same liquid with particles in it, that sort of fractures at this high rate in an angular and a brittle-like manner. So it sort of gives that in these dynamically similar experiments, it's sort of that rate where this material can fracture, and that might be one of the reasons why this basalt with these crystals is fracturing. So from these experimental results, what I got is that there is a 4 to 5 orders of magnitude increase in viscosity. Viscosity also is a function of rate of deformation. It also tends to fracture at a critical rate of deformation, which is about 1 per second from these experiments. But the question really is, can this be achieved in a natural setting? I do have all these measurements from the experiments, but really whether it is achievable in a natural setting. Also, the other observational constraints, such as the bubble number density and the average bubble size, and those, along with these crystal-rich basalts. So using this empirical output, then I used a conduit flow model to really figure out that whether it is possible to achieve this kind of strain rate in a natural setting during the eruption of this plinion, during these basaltic plinion eruptions. So here I am modeling the flow of magma in volcanic conduit, solving mass and momentum balance equations for bubble growth and magma flowing in a conduit. I am not showing any equations here, but it's a set of differential equations that I'm solving. If you're interested, I'll be happy to talk about it. The model overall has 2 scales to it. One is a bubble scale. So the bubble is growing due to decompression and diffusion. So decompression, as the magma rising, the bubble is growing because of the increase in volume of the gas. and also the diffusion of the volatiles that are present within the magma, because the volatile solubility decreasing, it's diffusing into this existing bubble. And then there's magma with suspended bubbles and crystals sort of ascending through this volcanic conduit. So that is the other aspect of this model. The initial condition for this model, I assume an initial radius and initial pressure. Initial pressure is based on the water content, a saturation pressure of water. And the bubble number density is coming from the observational constraints. That's from this textural analysis. The magma fragments at its surface that is given by my experimental result, that is 1 per second at that rate, where this magma expansion rates that reaches that criteria, it fragments into pieces, forming this gas pyroclast flow. And the top boundary is a choke flow condition that I'm using. So I'm just going to show the upshot of one of the typical results of this model here. And this is showing depth as a function of various model parameters. And the cartoon is sort of showing that what is happening here. But the upshot is that like the crystals are, the volume fraction of crystal is increasing within the magma as magma is rising. So the depth is decreasing. And that is causing the viscosity to increase. And the bubble is also increasing here. So this is the bubble radius, reaching to that average bubble radius that is observed in this pyroclast. And that is also causing an increase in the elongation rate. So the rate at which the magma is expanding. So here I'm using a bulk magma expansion that has that is not only an expansion or a growth of one single bubble, but the magma with lots of bubbles. So it has a phi term in it, which is the gas volume fraction. And so as this is the elongation rate is increasing, it's reaching that 1 per second criteria, and then it's fragmenting into pieces. That's sort of, and then the rest, it's the gas pyroclast flow that is again mass and momentum balance equation solving of that gas pyroclast flow from the fragmentation surface to the vent exit. But here I don't consider any bubble growth or exsolution because I'm interested in the fragmentation behavior. So that kind of shows that it is indeed possible to achieve this experimental the results that I got from experiments and also the observational constraints. So this integrated approach of looking into the class and having those observational constraints, doing laboratory experiments, and then adding this numerical modeling sort of gives at least some aspect of why these eruptions are taking place, why this liquid-like basaltic magma is fragmenting. So one is increase in viscosity. That is definitely important because that is causing this pressure to be preserved within the bubble so that bubble can act as a pressure bomb. But also it's very important that the rheological change from a liquid-like to a solid-like behavior in the presence of these crystals, which is probably the key for this fracturing behavior. So with that, but the thing is that like magma may also fragment in the presence of external volatiles. So in the next few slides, I'll be talking about the effect of external water on this explosivity of basaltic magma. Now, this has been, there has been a significant body of work that have looked into the effect of external volatile, external water like groundwater or seawater on the fragmentation of magma. Now, there are ongoing research efforts as to the effects of magmatic volatiles, that is volatile dissolved in the magma, and also these external volatiles and which have dominant roles and so forth. Here, I'm going to focus on some aspect of the effect of this external volatile or external water in this case. So on the left-hand side, this is a phreatomagmatic eruption. It's a subaerial, so just to have all of us on the same page, it's sort of like magma interacting with groundwater, and then it's a subaerial eruption, an explosive subaerial eruption that's happening. And this is a eruption on the seafloor where magma is interacting with the seawater. Until very recently, actually, it has been observed that this kind of explosive eruption do happen on seafloor as well. So as I was mentioning, that there has been a lot of work that have looked into the fragmentation aspect, either it's a field-based or theoretical and also experimental, that how magma may fragment in the presence of external water. Now, as the magma comes in direct contact with this cold water, it has this high temperature difference from the interior to the surface, and that creates a large thermal gradient that causes a differential expansion and a fracturing of the magma. But what is really this magma to water heat flux? How fast do magma cool? As it turns out that those numbers are usually taken from engineering literature, and not there is a lack of uh, the understanding of how fast the magma can cool in the presence of external water. And that is fundamental for this process, that how the external water may fragment this magma. So this key parameter, in order to understand how magma cools, I have done a high temperature laboratory experiments, and where this is remelted mafic rock, and it's submerged into a water. That's a schematic diagram, not to scale. And that has thermocouples in it, and submerged in a water that is also has thermocouples submerged in it. The temperature, time temperature data are recorded, and the experiments are recorded using the high definition camera as well. Then I also solved a transient heat transfer modeling with temperature dependent thermal properties. And the objective really is to have this time temperature data that I have from these experimental measurements to best fit those data with the model predictions. And this model has a boundary condition which has this convective heat transfer coefficient to find out that how what is the heat flux from this magma which is cooling in water, how fast it may cool. There are some interesting and very exciting dynamics, the interfacial dynamics that I have also observed, which is at this very high temperature when the magma is just this sample, which is like about 1100 degrees Celsius temperature or higher, it's sort of just submerged within the water. It creates this vapor film. So it's a film of water vapor surrounding this sample. It's stable for a few seconds, and then it breaks as the temperature of the sample decreases. It breaks and forms these numerous bubbles at that sample water interface. These bubbles then advance upward. So that's called a nucleate boiling regime. At a further lower temperature, there is no bubble present, and in the absence of any external or forced convection, it cools under free convection setting. Now, this vapor film has also been an important aspect of this studies, where it has been mentioned that the vapor film sort of helps this magma to interact and mingle with the water to be a more homogeneous mixture of the magma and water, so that it can fragment the magma into pieces in a phreatomagmatic style eruption. So it's important to understand how stable this vapor film is, and fortunately, we could see that. The other important outcome of this study is the heat flux. As I was saying, that the heat flux is typically formed from this nuclear engineering literature, but here what I observed, what I have found is that, so here is the heat flux as a function of superheat temperature, which is the delta TSH in this plot, which is the surface temperature of the sample minus the saturation temperature of the water, which is 100 degrees Celsius or 373 Kelvin. And so here, overall, the heat flux increases as the surface temperature increases. And there are three distinct regimes, boiling regimes. One is film boiling, one is nucleate boiling, one is free convection. And there are also these latent frost points. I will not have enough time to go into all the details, but latent frost points is where this vapor film breaks and this numerous bubbles form at this interface. So those points, those latent frost temperature are also pretty higher as uh, uh, compared to the ones that has been measured from in this studies using metal. For example, Fruit et al. 2009, where this was copper and silver that was the source, the heat source that was submerged in the water. Also existing study by Fari and Manga that shows that the results that I have are very different, but to remember that this is not these are non-vesicular and non-crystalline samples. Uh, the reason for having this is to have a reference to first understand how these different dynamic regimes are there, and what are the heat flux that can be expected in this setting. And there are, of course, observations that shows that there are lava flows and other subaqueous lava flows and so forth, where probably vesicularity or crystallinity may not be that important. But this also lay out a foundation for more complications to add in order to see that what kind of heat flux and other these interfacial regimes can be found out. So the key outcome of this study that is this film stability time scales, which is maximum 5 seconds as opposed to 50 seconds in some of this engineering literature that is out there. So it's a very short time scale where magma and water has to mingle if it has to, if that mingling hypothesis of photomagmatic eruption has to persist. Also, the latent frost points is high. As compared to the studies, the other existing studies, as I mentioned. The heat flux is quite high. It could be 4 to 10 to the up to 10 to the 6 watt per square meter. It is also a function of water temperature. So I vary the water temperature, and what I observe is that if the temperature of the water increases, that decreases this heat flux. So one of an earlier study that when I compared that with this heat transfer in air from a similar kind of sample and experimental setup, it shows that at least these heat transfer rates are an order of magnitude higher in the case of water. So relatively fine fragmentation is expected in the case of water if all else being same. So that's sort of I will quickly go into the next point, which is the eruption on Mars. So basalt is also most ubiquitous on Mars. So it's also important to understand how this basalt could be effusive or explosive on Mars. And some of this work that I have been doing are applicable here as well, that this influence of magmatic volatiles as well as the effect of external volatile. So one of the deposits that I have looked at, it's this pyroclastic deposit. This is Elysium Mons. It's one of the highest volcanoes on Mars, and this is the pyroclastic deposit very close to this Elysium Mons. This is also close to the InSight landing site. That is the lander that was sent by NASA recently, which is with international collaboration that has a seismometer on it, a seismic instrument on it that sort of measures, for the first time, measured Mars quakes. Interestingly, those Mars quakes are not too far from the pyroclastic deposit that I was studying. So this has implications because this pyroclastic deposit, it is very recent. It's a million year timescale, which is very recent for Mars. And that sort of also has implications for existing volcanotectonic activity, as well as the hydrothermal, magma hydrothermal interactions, which has implications for life. So this is the deposit that I had studied, which is very close to the Zunil, which is one of the well-known craters on Mars. This is within an area that is surrounding by lava flow in this area. So this is the Elysium Mons that I showed in the previous slide, and this pyroclastic deposit is in the southeast side of this Elysium Mons. And from the limited observational constraints, it has been proposed that this is a basaltic pyroclastic deposit. My colleague, David Tarbert, who laid that observational part, sort of has looked into the different aspects of this deposit. And this is a basaltic magma that erupted in an explosive style, creating this pyroclastic deposit. Now, one thing to remember that there are a very limited observational constraints because we cannot really have those samples and look at, and also the sorting of these grains and so forth are not also very well, it cannot be done that well either. But with that, then what I have done is that I used, again, the magma flowing in a volcanic conduit based on using those parameters that are suitable for Mars, using Martian gravity and the other temperature parameters and so forth, and the existing estimates of water content from meteoritic studies and so forth, to look at whether this can give rise to this explosivity of the basaltic magma. I'll not go into the detail of the result, but as I've showed the conduit flow modeling before as well, the upshot here is that using different criteria that are existing, it shows that it is possible for this basalt to fragment and create this pyroclastic deposit using just driven by these magmatic volatiles. Now, the other factor that I also have looked at is that the effect of this external water. In this case, in the area through some other observations, nearby areas, it has been observed that there could be a few hundred meters of thick ice layer present within this Martian regolith, 10 to 20% in the pore space of regolith. And so there could be, and there are other papers that have also suggested that there could be a scenario where this a dike, a magma-filled dike that sort of intruded but did not really have erupted. And so that could actually diffuse the heat and melt the ice within the regolith. And that water can then mingle with the magma to create this eruption, which is a phreatomagmatic style eruption. So that's sort of a study that I have done, the modeling of this thermal diffusion using a modified Stefan problem, and then looking at this ice to water phase transfer and how much water can be within a given short time scale, based on some of these empirical results from the terrestrial studies, this mass ratio between the water and magma. And that also shows that this kind of process can also supply sufficient water that could trigger this explosive eruption. So given the limited observation that I have, I cannot pinpoint one particular criteria, but it seems both are possible to generating this particular deposit. Also, using scaling analysis, just to check the time quickly, the scaling analysis, it shows that, again, using some of those the studies that are existing on terrestrial cases, because this deposit is very close to this Zunil crater, it's 10 to 15 kilometers away. And the timing of the Zunil, so that the age of Zunil is very close to this deposit. And the deposit also post-date in a way, the Zunil. So that sort of indicates that there might be some implications of this impact. And using the scaling analysis, what I have calculated that the seismic energy density that from the projectile velocity and the energy of the projectile and so forth that are suitable for Mars, the seismic energy density is much higher than the threshold that is required for triggering this eruption. So this is very exciting. It's because those Mars quakes that I was saying that it's sort of very close to that deposit. And if these are all true, then it might be possible that magma source that are still active today that has implications for this Mars quakes as well as other magma hydrothermal system. This is under review currently, this work. So some of the future directions, I'll end with this. That I am interested to pursue and excited about in the next few years. It's looking into this source to surface eruption and this three-phase magma dynamics in crustal reservoir as well as in the conduit, this plutonic volcanic connections. One thing to point out that although I have shown these basaltic eruptions as you might have noticed that these models are really based on fundamental physics, and by using the right kind of constitutive laws, it can be applicable to other magma compositions, which I'm interested to pursue as well. The effect of magmatic versus external volatiles, which is very important and an interesting avenue that I would like to pursue, and as well as in the next few years, I'm working on this comparison and both magmatic and external volatile driven on Earth, not on the moon, but on Mars as well, but comparing these three, as well as I will take it for the other terrestrial eruptions as well, this research. Okay, with that, I will conclude. I probably took a little bit of more time, but, and if you have any question, I'll be happy to answer.
Thank you, Pranabendu. That was fantastic. We have time for questions and discussion. Looks like Leaf has his hand up first. So we'll start with Leaf.
Hey there.
Yeah, hi.
That was an awesome talk. Thanks. I had a question about the first part. This elongation experiment that you did. So the fragmentation of the suspension, is that primarily a sort of large amplitude non-Newtonian effect, or could you, for example, get this with oscillatory elongation?
So the oscillatory part that I have done under shear deformation, so it's not really an elongation that I have done under oscillatory. That's a good point. That can be probably looked at. I think this was particular, like a first kind of a study in the sense of it, and so I'm interested to look at other aspects of it. So what you were referring to is that if there is an oscillation in this extensional deformation, what would happen to this sample?
Yeah.
Right. So if you have a repeated deformation, it's typically reduces and enhances the fracturing efficiency of the material. It has been shown much earlier by Dobran and others, so my intuition is that that's what is going to happen, but I haven't done that study. Yeah.
Cool. Thank you.
Kenny has a question.
Oh, I'd like some advice. Probably many of us here calculate viscosity with different models like Alan Whittington's models or Giordano model. And then we make a calculation based on crystal content to increase that viscosity. Do you have like a recommended equation that we should use to do this?
I don't have any recommended equation. I don't want to get into trouble, but I will just say that the equations, the formulations that you mentioned is for the melt viscosity, the viscosity of the silicic melt, and then using some other formulations depending on the interest, whether there is a presence of crystals or it's only bubbles that are present. So there are formulations that are present, and the formulations are not too different, the effect of bubbles or the effect of crystals or their combined effect. And it's an ongoing research direction. So there are a lot more work that are going on. And so for the melt composition, I would say choose that fits you best. But for the effect of bubbles and crystals, I would say you may would like to take a look at the Mather et al. 2013. That's an excellent review out there. That would be a good start, I would say. Yeah, thank you.
We have other questions out there? Well, I have a question, I guess, and I really enjoyed the last bit of the talk, discussing Mars applications at Elysium. And I was wondering, it looks like you can show that you can reach fragmentation conditions. But of course, a lot of places on Mars, we don't see that happening, right? So I was wondering if you could comment a little bit through your parameter search, how probable is it to reach fragmentation conditions on Mars?
Right. So the kind of the volatile content that I've used in the model, so that is also partly based on the existing estimates from these meteoritic studies on the Martian meteorites. So that is the best that is out there. So if you are reaching to, and I don't remember the exact number, but if you're reaching to a very low water content, you will just take that magma to the surface. So it will not vesiculate. So the one option is to have just no volatiles present in the magma. As I said, like if you don't have volatiles, you don't create bubbles. So it comes out as a coherent body, as an effusive lava flow. So it needs to have some volatiles, and the volatiles has to be a little bit higher than just zero because, or just a fraction of that, because that otherwise the saturation pressure that this water has, the water will exsolve. The result will show that it will exsolve onto the surface of the Mars, which means that once the magma is out there already. So by doing the parameter search, what I have found that to a very small degree that those mentioned in these Martian meteorites, it can be achieved using those criteria. And so my understanding is that like only if it's like people talk about the mantle heterogeneity on Mars and so forth, and also heterogeneity in terms of the wet versus dry interior and so forth. So maybe that could one of the reasons why some of the places you see an explosive eruption, which kind of is tapping this not depleted magma, and otherwise, if it is coming from this enriched magma, there are quite a few number of papers since 2016 that have showed experimentally that there are lots of water that could also present there. So yeah, so parameter search kind of shows that if it's either nil or a very low content, that would only not be able to create this explosivity. Otherwise, it is possible to have explosive eruptions on Mars as well.
And this is, you were looking at water primarily, or CO2 as well?
Water primarily, yeah.
Well, thank you. Brenna has a question.
Hi, that was a really neat talk. Thank you for doing that. I had a quick question on the strain rate model that you showed. When you show that the increase in strain rate kind of shows a brittle fracture, were you thinking that's from exsolution of lots of volatiles in the magma, or were you thinking that that was more of a very fast kind of conduit flow that caused the increased strain rate, or a combination of the two? Because for a basaltic magma, you would expect there to be, would it have enough volatile content to create that? I guess, sorry, that's a kind of a compound question, but.
Right, yeah, no, thank you for asking that question. The water content that I'm using in this model, so as Joe was asking the question, I'm using water. Of course, I'm interested to see the effect of other volatiles such as CO2, but the waters seemingly have more influence at the shallow depth. So it's a great question. So the water content that I'm using is from the med inclusion studies that are based on this Mount Terrera and Mount Etna eruption, those pyroclasts, and it has been found. So it is quite high, I would say 2 to 3 weight% of water. So that water, it's sort of causing this magma to vesiculate into bubbles. So the idea in this case, it's not the fragmentation due to a bulk fragmentation of the magma due to the elongation as it is rising, but the fragmentation as it is expanding due to vesiculation. So each bubbles are growing, so it's stretching the melt surrounding it, and that's causing this magmatic foam to really expand. Mm-hmm. And that's causing a rate, which is a function of the radius of the bubble, as well as the volume fraction of the gas within the magma. And that expansion rate is what I'm looking at. When that is meeting the criteria, that is where I'm in my model, I'm using that as this fragmentation of the magma.
Okay. Mm-hmm. And sorry, what packing fraction of your suspended material were you using in the suspension that showed the brittle fracture?
Right. So that's a great question. The thing is that there is a more or less bimodal distribution that I have found in this pyroclasts. And from my study on this elongated high aspect ratio crystals and sort of smaller equigranular crystals, it shows like about 70 to 72 weight volume fraction. percent of that could actually be the maximum packing, but I'm varying this. I showed you a typical plot that in my parameter search, I'm varying that maximum packing from somewhere from 60 to 80% or 90% to see the effect of it. Now, as
Right.
interestingly, because it is the viscosity is a function of the normalized packing fraction. So in a way that is, so whatever maximum packing that I choose, that does have some effect, but broadly the results, it's not going to change.
Okay. Did you see any sort of change with the different shapes insofar as which ones kind of created, you know, you would tend to go towards more elongate crystals for having a higher viscosity, but I mean, is that kind of what you saw?
No, let me quickly show you that plot.
Thank you. Sorry, I promise I'm done with questions after this.
No, those are great questions. Thank you for asking that question. Oops, sorry. Where was it? Yeah. So here it shows the maximum packing changes, but as I showed here that this data that actually are all different kind of particulate system, unimodal, bimodal, elongated, and spherical, they are all plotting on the same curve if you plot the data as a function of this normalized particle volume fraction. So that is the idea that if I choose a higher maximum packing or a lower maximum packing, it will have the time scale. It will change the time scale and the depth of fragmentation. But overall, the result that shows that can it reach that fragmentation criteria or not, that doesn't change.
Okay, awesome. Thank you so much.
Thank you for asking the questions. Yeah.
Looks like Anna has a question.
Okay.
Hi there. Can you hear me?
Yes, absolutely.
Thanks for that great talk. So with the Etna 122 BC eruption, my understanding is that it began with a sort of Strombolian style eruption of much lower intensity. Do you have an opinion about what sort of processes occurred to build it up into the Plinian intensity that it reached?
Yeah, that's a great point. So the models that I have looked at are steady state eruptions. So those are a steady state model. Those are based on the observation that the Plinian phase sort of went on for a few hours. So that's sort of a quasi-steady to steady state. So I'm modeling the Plinian phase only. So in my opinion, that I think this is really a great question, that how these different styles change from a Strombolian to, so one is definitely the rate. So if it's actually tapping the same magma from the same chamber, or as we now know that even for a basaltic volcanic province, for example, there could be multiple smaller chambers which are linked to each other. One thing could be a possibility that the magma that was sitting for a while, it sort of cooled a little bit, and as it has been shown by several authors that even by cooling by a few tenths of degrees can increase this crystallization, the rate of crystallization, or the crystallization that increases this interruptive crystallization. So one thing to look at if it is possible to figure out that what is the eruptive temperature of that melt is, and whether they are actually the same magma, or in the sense that whether they are coming from the same chamber, or the later one, the Plinian phase, has the start with a little bit lower temperature. A few 10 degrees of low temperature would have a huge impact on this undercooling and crystallization. So maybe the Strombolian eruption has not been able to have all these crystals, which sort of allows these bubbles to grow and not preserving this gas pressure. So that would be one thing to have a look at, I would say. If you have more information on that, what are the crystal contents, what is the bubble size and number densities and so forth, comparing those two would be a good place to start. And I'd be happy to talk more if you are interested.
Cool, thank you.
Well, excellent. This is probably a great time to, actually not, Thomas has a question here. He got it before I said it. So go ahead, Thomas.
Yep.
Thanks for letting me jump in there at the end. It was a good talk, Pranabendu. I thoroughly enjoyed it. I enjoyed speaking with you at AGU about some of this material as well. I just had a question about sort of your first part. If the bubbles, I understand the bubbles growing, bubble growth is easier in these basalts because of their lower viscosity. And if the bubble growth is what causes a high local strain rate, the stretching around these bubbles, that would be dependent on the ascent rate, correct? So my question basically is the need in a basalt anyway, is the need to ascend more quickly? Is that more apparent in basalts if they are to explode versus say more silicic melts, do you think? Because of their lower viscosity, I feel like they would achieve permeable outgassing earlier on because of coalescence or something like that. Either that or you increase the crystallinity to such an extent that you now delay the permeable outgassing. So the main question is, yeah, do you think we need to ascend even quicker in order for a basalt to explode versus more silicic melts, do you think?
Right. That's a great question, actually. So the models that I have, so there is an observation of this mass discharge rates, which is kg per second. That sort of goes into this model, which is typically, has typical numbers of about 10 to the power 7 to 10 to the power 8 for Plinian eruptions. That is how the Plinian is sort of defined. So whether it's a silicic or a basaltic, it's sort of that rate that are used. So the mass discharge rate is not going to vary too much because that is how it is defined. But the ascent rate, that is also it depends on the conduit geometry, of course, but that is also constrained by this condition of choked flow condition on the surface at the vent exit, and that sort of prevents it to get too high. So I would say, like, at the fragmentation, it might vary by a factor, but I wouldn't think that it would be too different for basalt versus in the case of silicic magma. Now, in the case of permeable outgassing, as you're saying, that it would achieve permeability much earlier, but the thing is that, like, for this kind of high rate of eruptions, it has been shown that the time scales of permeable outgassing and the time scales of the magmatic compression from those scaling analysis, it has not that significant effect in terms of the outgassing itself. So that would be also not too different as for these two cases.
Great, thanks.
Well, excellent. Thank you so much, Pranabendu, for an excellent talk, and everyone for a really great discussion. Mm-hmm. I think what we'll do is close out the big public session now, but if you do have questions from Pranabendu, if he has time, we'll stick around here. I'll keep the line open for a bit. But let's thank Pranabendu one more time. And also just note that we won't have a talk next week, but please join us for that Modeling Volcano Collaboratory discussion on the 15th of September. All right, thanks everybody.
Thanks.
How's Arizona?
That's good.
You had fires earlier in the year, is that right? Or
yeah, it was. Yeah, yeah, it was crazy. Like, I was like talking to some of the people, and they're saying, like, one side it's the virus, one side it's like the fire. It's like a movie. It's almost like yeah. So.
Well, this is fantastic work. You know, lots of different things going on. I was going to ask you, we'll maybe have some other discussion points too. I was going to ask you for the recent paper where you're looking at the heat transfer in water. Do you have a sense in that, you know, you had a heat flux related to the superheat. Do you have a sense for that, how much of that change in heat flux is associated with changes in thermal properties versus how much is the vigor of convection?
Say that again one more time.
So you have your plot of superheat versus heat flux, and I was wondering if you've been able to get a sense of how much that correlation is associated with just vigor of convection, so advective velocities versus just changes of thermal properties like coverage from vapor and that kind of thing.
Right. So the convection, you mean like in the water itself? Yeah. So the thing is that like when it's a vapor film, it's sort of like forming that sort of like the film surrounding the sample. Now that is the first regime that I showed. Sort of the convection, the free convection part comes much later, at a lower temperature of the sample, where you do have this vigorous convection to more turbulent to laminar convection. But I did not look into that aspect of it in detail. I was more sort of interested in this vapor film and nucleate boiling, that there's lots of bubbles that are forming at the surface, because those are happening at a higher temperature, like 200, 300 degrees Celsius sample temperature and larger, which are more interesting for application purposes in the for our case. And so this convection's happening at a much lower temperature where it's turbulent to laminar. But I also did not, I focused on mostly how the temperature, it is driven by what's happening in the water, as well as the thermal properties of the sample itself. So there is an edu abstract that I have. I'll go into, and I'll talk more about the dynamics in the water itself. So
okay, that's great.
Yeah, it's fascinating, like how this regimes change from this film boiling to this bubble nucleation and the nucleate boiling regimes, and these are really interesting stuff.
Have you I'm probably very hard to do this, but have you experimented with the stability of the vapor film when you have some external velocity or different shapes of particles and that kind of thing, or?
Right. No, not really, because I haven't. I mean, there is no external flow here. So I have a study that is what I'm going to present at HU, that I have had this external forced convection setting, but I am not looking into the vapor film itself, because what I have found is experimentally it's quite challenging to have that vapor film at that location, particularly to have, and what's happening during the flow condition. So what I'm going to I'm focusing is this nucleate boiling regime, which is sort of this intermediate temperature. So for example, let's say a scenario where a submarine lava flow, and it sort of has already flowed for a while. So the vapor film is only stable for a few seconds, which have more implications for the phreatomagmatic cases. But as it's flowing, it sort of goes into this steady state, and that where it's this two-phase sort of bubble nucleation and this nucleate boiling regime that sort of picks up. So that is what I'm looking into. But yeah, thanks for that comment. It's something that I'm very interested and I've thought about, but haven't really looked at that yet.
Yeah, that's great. That's all really great work. Other thoughts? I don't want to.
Yeah, hi Pranabendu. That was a really good talk, and I felt bad that all of Alan Whittington's students were sort of piling on to you at the end of that discussion part there. So I would save my question till this part. But I really liked how you quantified, all the various effects of the rheology of basalts, before fragmentation, and like. But I was curious, like, as someone who works on rhyolites, like, what role does temperature play? Is it possible that the basalts that fragment are just maybe lower temperature, and therefore their rheology is a little bit more viscous, closer to the more silicic stuff, or,
Yeah, well, the viscosity change due to change in the temperature of the basalt. So that temperature is usually measured, and it has been based on this petrological studies based on the crystals that are present in these basalts and so forth, that what is the eruptive temperature for this basalt. So that's sort of around that range of 1100 degrees Celsius and so forth. So if you go to too low a temperature, then it would probably become a basaltic andesite or andesitic magma, because it's then crystallized all this high magnesium, high calcium crystals that sort of like now changes the composition of the magma itself. But yeah, I mean, changing temperature could also increase the viscosity. That has definitely implications, but basalt has to be basalt, and that is only possible if it above certain temperature threshold.
Okay. Yeah, because I know, I mean, basalts nucleate crystals a lot faster too. So I guess little changes in temperature probably would be overcome by the crystallization kinetics faster than, say, in a rhyolite, because you can change the temperature of a rhyolite over a much bigger range before crystallization occurs. So, okay, all right, that's cool. Thanks.
Thank you.
Other last thoughts for Pranabendu before we sign off here?
I think thank you for giving me the opportunity, and I think yeah, it was really great. Thanks for.
Oh yeah, thanks for a great talk. That was fantastic, and yeah, let's chat more later on. I'm excited to see some of this other stuff come out. I'm excited about your AGU stuff too, and more of the Mars stuff. It'd be great to talk more about that.
Sure. And is this chat going to be?
Yeah, it's great. So that we'll have a recording. I'll send it to you, and provided it's okay with you, I'll post it on the Slack channel too. But the nice thing is the chat, which has a lot of great comments, a lot of nice comments about what people said. That's also recorded too, so you can take a look at that.
Okay. Okay. Sounds good. Okay. Thank you.
Well, yeah. Have a good afternoon, and chat with you.
Thank you, everyone. Yeah.
Cheers, everybody.